Hey Jeff, are we skipping 6.5?
Yes, 6.5 is not part of this course, so we're skipping it.
Thank you.
So one of the things that is kind of annoying for a lot of Calc 1 students is that even though there's a product rule for differentiation, there's no product rule for integration. That is, I can't integrate x squared times cosine of x by distributing this and go, oh, that's the integral of x squared times the integral of cosine of x. It just doesn't work that way. The closest thing to a product rule that we have for integration is an integration technique called integration by parts. So we're going to spend a lot of time in chapter 7 learning different tricks of integration, kind of like you learned tricks of differentiation. Now we're going to learn tricks of integration. So let's take a look at the product rule for differentiation. Derivative of the first times the second plus the derivative of the second times the first. Okay, so that's our product rule. Now, one thing that you should learn for sure in Calc 1 was the operation that does the opposite of differentiation. What operation is it that is the opposite of differentiation? What does the opposite? Say again?
Would it be taking the antiderivative of something?
Yeah, taking the antiderivative, which for us was integration, right? So if we integrate our product rule, then that's integrating a derivative. Those two operations are inverses of each other. They cancel each other out. So what you're left with is u times v. Yeah, u times v. And I'll just leave this kind of like it is, except I'm going to rewrite it a little bit. I'll rewrite it as u times, well, it's u times dv plus the integral of v times, let's see, v times du. So I'm making kind of a little bit of shortcuts and such, but let me rearrange this one last time by moving this to the other side and get u times v minus integral of u dv, or it's going to be v du, equals the integral of u times dv. This must look like a real big mess to you, but it's actually a very clever technique to use to kind of rearrange things and see if you can't get the antiderivative of something. Now, the way it works is that in your integral, you're going to try and make two identifications. You're going to try and figure out what could u be and what could dv be. If you can figure out those, then you have a chance of rearranging things, and hopefully what you're left with, this v du term, will be easier to integrate. So we'll play around with this and see what we can do with a bunch of examples. So in each problem, you're going to have to make two identifications. You're going to have to identify a u and a dv term. And I wish I chose something with a little bit more contrast than that. How about that? There we go. So we're going to have to identify both of those things and see what happens. So let me start with this example. So we're going to be asked to find the integral of x to the fifth ln of 3x dx. And you look at that and it's like, well, wait a minute, I have no idea. That's not one of our basic forms. You're not going to get away with just a cheap u substitution in here. So you pull out the big guns, the Calc 2 guns. And that is, let's make a little substitution, or let's see if we can't do this by integration by parts, not by substitution. So one of these is going to have to be u, and one of them has to be dv. So u and dv. Now, when we have u, we're going to differentiate it and get du. If I have dv, I'm going to integrate it to get v. So when you're looking at these two terms and trying to decide, well, what am I going to let u equal and what am I going to let dv equal? Well, one of these you're going to have to differentiate and one of them you're going to have to integrate. Whatever you integrate has to be something you can find the antiderivative of. And whatever you differentiate, it's nice if it doesn't get any worse, but sometimes it will a little bit. But pick something that you can integrate and something here that we're going to differentiate. And maybe that when we differentiate it, it's going to get simpler. What's going to work in this case? Well, if I let u equal ln, if I let dv equal ln of 3x, I have no idea what the antiderivative of ln of 3x would be like. That'd be a problem in itself. So let's let u equal ln of 3x. What would dv equal? Well, dv's got to be the rest of this. And the rest of this is two things. It's an x to the 5th and a dx. So let's put both of those in. X to the 5th dx. Now the derivative here should be pretty easy. Derivative of natural log is going to be 1 over the function times the derivative of the function. So what's the derivative of 3x going to be?
3.
Times 3. So I'm going to 1 over x here for my du term. How about the antiderivative of x to the 5th dx? When I integrate this, what do I get? Anyone?
X to the 6 over 6.
X to the 6 over 6. Thank you. So now we got to put it together into this formula. The first thing I need is u times v. So I need that. So let's write that out here. U times v is going to be ln of 3x times x to the 6th over 6 minus integral of v du. So v times du. Actually, these two, right? So it's going to be x to the 6th. You know what? There's a dx term here. dx. So let's put that in there. So I get x to the 6 over 6 times 1 over x dx. Yay. Almost done. This is going to clean up a lot. ln of 3x over 6 times x to the 6 minus 1/6. See any cancellation here? X to the 5th. And we can integrate that. In fact, we just did. So, yeah, I think I prefer to write this out in front. X to the 6 ln of 3x over 6 minus 1/6 times x to the 6 over 6. Let's not forget our constant of integration because I guarantee you WebAssign won't forget it. 6 ln of 3x 6 minus x to the 6 over 36 plus c.
I'm sorry, you lost me. Did you take x to the 5th dx and then you got the antiderivative, which is x to the 6 over 6?
Yep.
Plus the constant. Okay, thank you.
And then I just multiplied the 1/6 and the 6, x to 6 over 6 together.
Okay, very well. Thank you so much.
Yep. Thank
Can I ask a quick question?
Please.
Can you please go over how you know which one's the du term and which one's the v term?
That's a great question. So I want you to do an experiment here for me. Everybody's got a special skill. It's like something you're really good at. It's like, oh man, I'm really good at this, or I can do this really well. Think of your special talent. How did you get good at your special talent? Everyone knows it.
Repetition.
Repetition, practice, a lot of work. And that's it. It's just a lot of work here. So, you know, if we tried it the other way, you'd run into a brick wall pretty quickly. Because if I let dv equal ln of 3x dx, do we know how to integrate this? No, I don't know an antiderivative, not off the top of my head anyways. In fact, actually, a little bit later today, we'll try this. And it's a good question. And one of the problems we're going to go over today is one that I saw on WebAssign. But just so you know, it takes me probably a good half hour or more to create your WebAssign assignments. And that's because I don't just click a bunch of boxes. I look through the problems and make sure that they are reasonable and reflect things that I'm teaching or will teach. And one of the problems that we're going to get to was one that I looked at that I'm like, wow, this one's kind of cool. Because a lot of times when I look at these things, I know what to choose for U and DV. But that's because of experience. You just need a lot of practice on these. But what you want to keep in mind is that you need to be able to find an antiderivative for DV. So that kind of limits things right there. And there's a lot of other tricks that I hope that you'll see as we go through this. But, you know, the basic answer to your question is a lot of practice. And yeah, I wish I could give you a simpler answer. I can't. Okay. Yes.
When you plugged everything in, did you only plug into like only the left side of the equal sign, I guess?
Correct. Yes. So this is the integral of u dv, and then I filled in the left-hand side. So this is u times v minus the integral of v du. That's what this is right there. Does that help out?
Yeah.
Okay. Thank you.
When you were doing the d sub u, where'd you get the 3dx from?
Well, when you integrate, or excuse me, when you differentiate this, it's 1 over u times the derivative of u, or 1 over the inside times the derivative of the inside, just applying the chain rule. So when I differentiate this, it's 3 times the derivative of x. So, I mean, technically this is du by dx, and then I multiply by dx on both sides, and that's where you get the dx from.
Oh, thank you.
Yeah, no, appreciate it. Questions are really helpful. Thank you.
For choosing U, I heard the previous question. I remember reading somewhere that there was this sort of acronym that you would follow by to choose U. Does that help at all?
I don't know what that acronym would be, but if you want to run it by me, I
think it was like you choosing the U in the order of like logs, then inverse, then algebraic, then trig, then exponential.
Boy, I have to think on that one. Doesn't sound bad. Doesn't sound bad at all. So, yeah, but no, I wish in that sense I had something for you. I actually do have something for you that's kind of cool that we'll get to in a couple examples. But let me do some more examples first. One thing that you like to see when you differentiate is that you get something that's simpler, or at the very least, it's not any worse. I mean, that's what you'll like to see. May not always see it, but those are a couple general guidelines, is that you want to pick something for you that when you differentiate could get simpler. Those would be your polynomial terms. And you need to pick something that you can integrate for your DV. So let me keep going. the integral of 5x e to the negative, or e to the 2x dx. There we go. Let me start by rewriting that a little bit. 5x e to the negative 2x dx. And that puts it a little bit more in the form of, you know, hopefully a u times dv. Now, this is not something we can integrate directly. We don't have a product rule for integrals. So the best we can hope for then would be to set it up as something is my u and something else is my dv. Now, basically, we're looking at a couple different possible terms here and here. Now, when you differentiate things, that is, whatever you let u equal, it's nice if they get simpler. And when you integrate things, they have to be things that you can integrate and they get no worse. Let's look at both of these and ask yourselves, of the two of them, which one's going to get simpler when you differentiate it?
5x.
5x, yeah, 5x. And then the rest of this would be e to the negative 2x dx. But 5x is a good choice for u because that means du is going to be 5 dx. And v is something that you can integrate. Now, let me share with you something that I do for these problems. Because here, if I was to integrate, technically, you need a u substitution to integrate this, right? I don't want to slow down my work on a problem like this to do a u substitution. So let's think of something related but different. If I differentiate this, I'm going to e to the negative 2x back times the derivative of the exponent, right? So what's the derivative of the exponent?
-2.
Negative 2. So if I differentiated this, it'd be e to the negative 2x times negative 2. But integration is the opposite operation. So what's the opposite of multiplying by negative 2?
Dividing.
Dividing by negative 2. So the shortcut on this, and I don't teach this and say this to my Calc 1 students, but the shortcut for you is to think about differentiation that would result in multiplying by negative 2. So integration will divide by negative 2. Or of course, you could write that as negative 1/2 e to the negative 2x. But I strongly suggest you get comfortable with that little mental mind trick, because if you have to sit down and write out, okay, let's let, I don't know, some other variable like s equal e negative 2x and then do all that u substitution, it's going to really slow you down on problems like this. So it's up to you. We'll practice that some more.
Mr. Parent, I'm sorry.
Yes, please.
Does that only stand true for E?
No, you can do that for other things like sine of 2x or cosine of 2x. You can work it for those things as well. But
Okay, so just divide by the X variable.
divide by really the coefficient of the x. But you got to think about what happens when you differentiate and then do the opposite to integrate.
Okay, and then one more thing. In comparison to the last example and to this one, the U is the first term. So basically, U is just going to be the most easiest thing to differentiate.
You like U to get easier when you differentiate it, and V has to be something, or dV has to be something you can integrate it, and hopefully it doesn't get a lot worse. So that'd be what I have to say about that.
So if it gets messy, then it's wrong.
Not necessarily. I mean, there's one that we're going to do it's like, oh, In fact, it's the one that I did when I said, most of these I can just look at them and know. This one I couldn't. This one I had to tinker with a little bit, but we'll get there.
Okay, you got it. Thank you so much.
Mm-hmm. Okay. So let's put this together. Remember, we're going to let that equal, that's going to equal u times v minus the integral of v du. And what's that going to place out or turn out to be? Well, u times v is going to be 5x times negative 1/2 e to the negative 2x minus the integral of v du, which would be your minus 1/2 e to the negative 2x times 5 dx. And it's nice that we have that dx here. It causes personal distress when my calc students don't write the dx. So please have pity on me and write the dx. Thank you. Okay, let's clean all this up. I'll write that as negative 5/2 x e to the negative 2x. The minus and the minus give me a plus 1/2 integral of, actually, you know what? We should bring the 5 out in front too, shouldn't we? Let's get rid of all those constants. So make that a 5. And that leaves me with e to the negative 2x dx. Okay, well, did we get anywhere? Did we make any improvements? Can you integrate that? I hope so. It's going to be 5/2. This is like what we just did for my dv term. If you were to differentiate it, you'd end up multiplying by -2. But because we're integrating it, I'll end up dividing by -2. So it's going to be e to the negative 2x over -2. Let's not forget a constant of integration. Probably should clean this up just a little bit. The -2 times a 2 is going to be a -4. Let me put the negative out there. Actually, there's a couple things you could do. You could factor out a negative 5/2 e to the negative 2x. Let's see, do we want to do that? Maybe I'll simplify it in 2 different ways. So this would be negative 5/2 x e to the negative 2x minus 5/4 e to the negative 2x plus that ever-loving constant, like that. And that's fine. I'm sure WebAssign would accept that. If you looked at their answer, they'd probably factor out the negative and the 5/2 e to the negative 2x here. So, or negative 5/2 e to the negative 2x. If I factored out the negative and the 5/2 term, that would leave behind x. Let's see, b plus. The negative's gone and be left with a half, x plus a half, plus a constant. So that'd be an alternative way to write that.
I hope something like this isn't on WebAssign. It's very hard to write.
Do you want me to tell you the bad news now or later?
Hit me.
Yeah, let's get rid of it now. These are the easy ones.
Oh god.
Sorry. All right. Well, how are we looking on this one, though? We're looking okay with this? All right. The crowd bubbles over with enthusiasm. Yay.
You're just very prone to making mistakes here.
It's the nature of the beast, yeah. Yeah. It's a pain. There's no
I have a
doubt
quick
about it.
question.
Yeah, please.
If we have like a couple numbers wrong, but like the setup correct, will you still give us partial credit?
Absolutely. So one thing I'm going to be doing different this semester than I did last semester is that the tests aren't going to be on WebAssign. I'm going to have proctored. You're going to be on Zoom, but I'm just going to have regular test. And if you make little arithmetic mistakes here and there, look, I'll spot them and I'll take off some points. You're not going to lose like all the credit. So it's not going to be like WebAssign where it's all or none. Like if you forget the C, oh, you got it wrong, which, at that point you just want to pound the computer into dust. But what I like about, that idea of just giving you regular tests is that I can be more forgiving when I grade them. I like to give you credit for what you show and what you know. And keep in mind, I'm going to have a little bit more freedom in designing my own questions. So sometimes I'll be set up this, or what would you let U equal? What would you let DV equal? That kind of thing. I can do other things other than just say, solve it. Now keep in mind, there's going to be plenty of solve it, but it's not going to be everything. Some problems are just going to be set it up. Okay. Okay. Anything else? Okay. So as a special bonus for you guys, let me show you something called the table method. And this is really cool. This is a Jeff special. You're not going to find this in the book, I don't think. I don't know, maybe you will. But the table method is for when you have things that are just nice polynomial type terms times a sine or a cosine or an e to the 2x. So this is our third example of integration by parts. Integral of x to the fourth times, let's do cosine of 2x dx. Now, when you look at this, there's no quick U substitution that you can do. There's no good trig identities that we can use. You're just stuck. And since we don't have too many integration techniques, you start thinking integration by parts. Now, here's what's going to happen. We're going to have to figure out a U and a dV for both of these. So why don't you take a second and see if you can figure out just U and dV. Don't write anything else. All right. Rochelle, I think I tried calling you earlier, but someone beat me to the punch there. What'd you get for U and dV? No, Rochelle?
I think cosine of 2x would be U.
It could be, but what's going to happen if you differentiate x to the fourth power? You're going to get x to the third power. So you're lowering the power, and it's in some sense becoming an easier function. So let's do x to the fourth power. But thanks for trying. And then that leaves dv is cosine of 2x dx. Now, like I said, what's going to happen when you differentiate here? Let's just list the derivatives. What's the first derivative? Michael?
4x cubed.
4x cubed. That was a sophomore, Michael. Try another one. Differentiate again.
12x squared.
12x squared. Awesome. Keep going. You're on a roll.
24x. 24.
One more.
That's 0.
0. Awesome. Awesome. So there's all the derivatives all the way down. So it's nice having this term here because you're going to differentiate all the way down. Now, the thing about this problem is that when I do my u times v and v to u, I'm going to end up with an integral kind of like this with an x to the third term. And then I'm going to have to do integration by parts again on that one. And then integration by parts again on this one, and then so on and so on. It becomes a pain. So with integrands like this, where you have a polynomial term times a sine, a cosine, or an e to the x, something that cycles and is easy to integrate, we can use the table method. Now, for that, I'm going to need some antiderivatives going this way. So let's think about the antiderivative here. So I know it's going to be a sine of 2x. So I know it's going to have to include sine. It's going to bounce back and forth. But if I was to differentiate this, I'd end up multiplying by 2x, or multiplying by 2. So when I integrate this, I need to divide by 2. Now, let's check one more thing. Is the derivative of sine cosine?
Negative cosine.
We're not going this way, we're going this way. Derivative of sine is cosine. So we're okay going this way. Now, let's find the antiderivative again. So I'm going to switch from cosine or sine back to cosine. I'm still going to have that 2x. And instead of multiplying by 2, I'm going to have to divide by 2 again, or multiply by 1/2. I'll have 1/2 times 1/2, which is 1/4. Now, do I have everything right? If I differentiated this, would I get this? The
Wouldn't
answer
it
is
be
Negative. It would be negative.
yes. So I got to put the negative in there. Now, your turn. Let's do one more. Actually, a couple more. Integrate this yet again. So it's going to be a sine of 2x. And then a fraction here.
1/8 sine of 2x.
1/8 sine of 2x. Should be negative or positive?
Positive.
Well, when you differentiate sine, what do you get? When you differentiate sine, you get cosine, right?
Be negative.
And the only way that negative is going to stay there is if I have the negative here to begin with. So I want that to be a negative 1/8 sine of 2x. All right, good job. Try the next one. We need to do this 2 more times. So try and find the antiderivative here and here again. So 2 more.
Would it be 1/16 cosine of 2x?
Nice. 1/16 cosine of 2x. Good, because derivative of cosine is negative sine, so I want a positive here, so when I differentiate, I get the negative there. Beautiful. And last but not least, it's going to be a sine of 2x. I'm thinking you're seeing the pattern here. It's going to be a 1 or a negative 1?
1.
1. Good, because derivative of sine is cosine. Excellent. We're 90% done right here. This would be a brutally long problem if we weren't using a nice little trick. Are you okay with our tricks to get our DV lists? Because that's key in doing these things.
Yeah.
All right, cool. Now, here's the trick. We're gonna multiply all these together in this way. Now the question is, why can we stop here? Well, if I did another one, it'd be 0 times something, right? So there's nothing I need to worry about there. So I said we're going to multiply here. There's one last little thing. Plus, minus, plus, minus, plus. So it's going to be this times positive 1 times this. In other words, I'll have x to the 4th over 2 sine of 2x. Then this times this times this. It's up to you. Do you want me to do the simplification here? The 4's cancel. Or I could just write it out and we'll simplify in the next step. What works for you? Simplify it now. Okay. The 4's are going to cancel. Negatives are going to cancel. I'm going to be left with x cubed times cosine of 2x. Let's look at this one here. Here times here. 4's will cancel. 4 goes in there 3 times, here 2 times. Positive times a negative is going to be negative. So negative 3/2 x squared sine of 2x. Then down to here, positive times a negative is going to be negative. 8 goes into both of these things, so it's going to be 3 and a 2, so minus 3/2 x times cosine of 2x. And the last one is going to be plus, right? It's all going to be plus. 24 and 32 share a common factor of 8. It's going to be 3/4 of sine of 2x. We're all done. So now you can put plus a constant. Okay, so there's your table method. The alternative to this is, as you keep on doing your integration by parts, every time you do your VDU term, you have to do another integral of parts. And it just gets really, really messy. So this is actually, for the work that we did, we got a lot out of it. But it's a nice trick, and I'll show you another one like it. We'll do another example here.
Wait, so you can only use this for like trig functions, or like when you multiply by trig functions?
I always suggest you use it for things like this. Some polynomial of x times cosine of x, or polynomial times a sine of something like this, or a polynomial times e to the bx dx. So these would be good problems for the table method, where you've got a polynomial. And the thing about polynomials is that when you differentiate them enough, eventually you're going to get down to 0, like we did here. All right, eventually we get down to 0. So it's going to disappear. So that's going to be your u part, and this is going to be your dv part in those types of problems. So these types of problems are beautiful for the table method. Can you use it for other things? Yeah, absolutely. I've had students in the past get really creative with the table method and apply it in ways that surprise me, to be quite frank. Great question. Anything else?
This method kind of just confuses me. So if you would have done this like the normal way, you would have ended up with the same answer too.
Oh man, you have no idea how much work the normal way would be. Let me just give you a little sample of the normal way. And I'm not going to do the whole thing. Tell you what, I'll let you do the whole thing the normal way for extra credit. No, not for extra credit, because I don't want to grade it. I changed my mind. x to the 4th. It's just painful. It really is. Cosine of 2x dx. So, our u and v work the same. So it's going to be, let's see, we got u times v. So it's going to be x to the 4th over 2 sine of 2x. And then we're going to have v du. So that's going to be v du. So minus the integral of 4x cubed times 1/2 sine of 2x dx. And so now you got to expand this with integration by parts. So now you got to say, okay, well, that's really, 2x cubed sine of 2x. So then you got to go through with your, all right, well, let's let u equal this, and this equal dv. You got to do that again. So that expands into this, u times v. It's going to be what? 2x cubed times v is going to be the antiderivative of that, so it's going to be -1/4 cosine of 2x minus the integral of v du, which would be -1/4 cosine of 2x times the derivative of that, which is going to be your, actually derivative of this, which is going to be your 12x cubed, 12x squared dx. And that's just 2 of these. You gotta do like 4 more. Man,
It's just like the chain. So it's like the chain rule for integration, but like on steroids.
I think it's even worse than the chain rule. It's just because then you have to do this again. You have to do it here, and you have to keep track of all your negative signs because this negative sign distributes to everything here. And then when you do brackets here, you have a negative sign distributes to everything here. Wow. It's just try it. Try it and get back to me. If you like it, go ahead.
My other question was why you had to go and like all the way down to 0. So is that because it usually breaks up like that? You would have to do that normally
Well,
for these.
we're only going to do this for polynomial functions here. And the reason that it works is that you can stop, right? Because at 0, I mean, let's think if I did this next one, it'd be -1/64 cosine of 2x, right? But then if I did 0 times that, it's just 0. So
right.
Everything would stop here. Now, one thing that's true is that when you're doing these integration by parts, if you start out with something as your u, you want to stick with it. All right. So if in one part of the problem this is u, and this is your dv, if you have to integrate again, don't let all of a sudden the cosine term be your u and then the polynomial term be your dv. You want to stay consistent within those things. So just keep on working with the same types of problems for your u and v, u and dv. Okay, let's do another one like this.
Sorry,
Yeah, go ahead.
Is it always like plus minus plus minus plus for the pattern?
Yes, always plus minus. It always starts out as a plus, and then it alternates. So plus, minus, plus, minus, plus. So yeah, it always alternates. Yep. Okay.
I'm sorry. Why it has to be a plus and then minus, plus, minus? Like, what is why?
So what's happening is that when you do this, if you were to do this out the long way, so the original terms, there's a minus, but then on the next term, you have the minus of a minus. So then that becomes a plus. And then if I expanded this, then the minus here, uv minus integral v du, minus and the minus, you keep on distributing these negative signs to what follows. And when you do, that creates an alternating pattern throughout your problem. So I guess in the future, what I should do is I should have one of these done out longhand so you could see the difference. But if I did, it would take up this whole page. It'd just be massively ugly. But to your question, when you keep on doing these integration by parts things, that negative is always going to have to distribute, and it's always going to be changing the sign between these things.
Okay, thank you.
Mm-hmm. Let's do another one. So let me do another table method one. Let's see. Integral of x cubed e to the negative. Someone throw out a small constant for me. And we'll do 5. All right, sorry, I got that too late. But I'll use it the next one. 9 here. So this is a polynomial times some function of e. That's a good one for our table method. So let's see if we can't set up a table method for this one. When you set up these table method type problems, you want to let u equal your polynomial term. So we're going to let u equal x cubed. dv is going to be e to the negative 5x dx. So the first thing we're going to do is we're going to differentiate these things. 3x squared, 6x, 6, and 0. And the 0 is a nice thing that tells us, okay, we can stop. Let's work with the antiderivatives here. Now, if I were to differentiate this, I'd have this times what? The derivative of this would be e to the negative 5x times negative 5. But because I'm integrating, instead of multiplying by negative 5, I'll divide by negative 5. Or I can multiply by negative 1/5. And then I got to do the same thing again. So what number am I going to put here?
25.
Good, 25. And each time, instead of multiplying by negative 5, you're going to multiply by its reciprocal, negative 1/5. So negative 1/5 times this is 125 times negative 1/5 again is negative 1 over 125. And we'll do one more time, so that's going to be 1 over 625 e to the negative 5x. And I can stop there because I got down to the 0 level here. Okay. So, where'd my pattern start?
Positive.
Positive, negative, positive, negative. And that's just a product going down. So x cubed times this is going to be negative x cubed over 5 e to the negative 5x. Positive times a negative is going to be negative, so it's going to be negative 3x squared over 25 e to the negative 5x. Positive times a negative, no, that'll be negative again. So negative 6x over 125 e to the negative 5x. The last one is negative 6 over 625 e to the negative 5x. After all that lovely work, please don't forget your constants. Now, if you wanted to, there's the greatest common factor that you could factor out, but I'm not going to bother.
Is WebAssign particular about what kind of answers you give, or will it accept something that is like equivalent?
It should accept that. Yeah, but keep in mind on WebAssign, I do give you 3 attempts, and you know, if you don't do well on the first one, then try it again if you figured out your mistake. If after your second attempt you don't get it right, I think a couple of my students from last semester who are in this class this semester had a smart trick, and that is they go to the tutor and make sure they got the problem right before they entered in their 3rd try, because you do get points for doing well on the homework. So you might want to make sure that that last try is a good one.
Like the WebAssign tutor?
No, our supplemental instructor, Mimi.
Oh.
All right. And her hours were emailed to you, and they're also posted on the announcements page of D2L.
But also on the WebAssign tutor or the practice problems, it'll sometimes show you how the answer should be formatted. So that could work also.
Thank you. Trying to think. There are some problems where WebAssign will have a little button that says Ask the Tutor. So you could do that one as well. Here's one that I picked and put in your homework, mostly because I looked at it, I'm like, oh, hey, that looks cool. I don't know how to do that one. And I had to think about this one for a little bit. 5x, e to the 2x. So we're going back to more of a traditional integration by parts. It's just amazingly flexible in terms of the things that in a variety of stuff that you can integrate now. And I had to divide this problem up into 2 parts. Now, obviously, the dx is going to go with the dv because we need that to integrate. And I toyed around. I tried a lot of other things. Let me see that. No, I didn't save my scrap paper, but I tried 5x because when I differentiated that, I was like, hey, that works out good. But unfortunately, when I differentiated that, that leaves e to the 2x over 1 plus 2x squared dx. I had no idea how to integrate that. So that choice didn't work too well. And eventually what I said is, all right, well, I need something I can integrate pretty easily. And one choice is 1 plus 2x squared dx. Now, if I let that be my dv term, what's my u term? Well, my u term is 5x e to the 2x. And let me be clear about something. In some problems, there's different choices for u and dv that'll both lead to the correct answer. So it's just going to depend on the problem. Now, with those choices, let me help you out with the v term. You can integrate that with a little u substitution. You'll end up with minus 1/2 times 1 over 1 plus 2x. And here, when you differentiate this, you have to use the product rule, which is kind of annoying. It leaves you derivative of the first, that's just going to be derivative of x is 1, e to the 2x, plus derivative of the second, that's going to be 2 times derivative, well, 2 times e to the 2x times 5x. So this is your first and second. So that second term here is going to be 10x e to the 2x. And it's worth noting here that if I factored out the common factor of 5e to the 2x, 5e to the 2x would leave behind 1 plus 2x. So that's my du term. All right. So u times v minus the integral of v du. Let's put all those together. U times v. It's going to be 5x e to the 2x times negative 1/2, or negative 1 over 2 times 1 plus 2x minus the integral of v du. And here's where it's really nice that you took the time to clean up the du term just a little bit. So it's going to be minus 1/2 of 1 over 1 plus 2x times 5e to the 2x times 1 plus 2x dx. Here's that good news. Those two cancel. Now, this, I'm going to write a little different. I'm going to put this all up in the numerator. So it's going to be minus 5x e to the 2x over 2 times 1 plus 2x plus, let's take the 1/2 out in front. Negative cancels that, made it a plus. 1/2. And I'm left with the integral of 5e to the 2x dx. Well, the good news is I can integrate that. So it's going to be negative 5x e to the 2x over 2 times 1 plus 2x plus 1/2 times 5 times, when I integrate that, it's going to be e to the 2x over 2. Now, I'm pretty sure that WebAssign should accept this. One half and 1/2 gives me 1/4, so 5/4 e to the 2x, like that, plus a constant. WebAssign should accept that. However, that wasn't the answer that they put on WebAssign. And I was greatly distressed because I was so proud of myself. I'm like, oh, cool, I figured it out. But it didn't match the answer in WebAssign. What they did in WebAssign was they got a common denominator by multiplying, well, I need a 4 here, so I can multiply this by 2 over 2. I need 1 plus 2x here. I don't know how much of the nitty-gritty you want to see, but when it all simplified out, it was 5 e to the 2x over 4 times 1 plus 2x plus a constant. That's the way it ended up. Whew. Okay, beautiful, beautiful. I think you worked pretty hard. You deserve a break. So I'll see you in 6 minutes. And part of those 6 minutes, I'll fill in the details here. So if you distribute that, distribute this, end up with negative 10x e to the 2x plus 5 e to the 2x plus 10x e to the 2x all over 4 times 1 plus 2x. And those two cancel. All right, get yourself a good stretch. We're in the home stretch.